Welcome to Demystifying Science. We have a real treat for you today. We are following up on a whole line of investigation we've been scraping away at. A couple weeks ago, we had NASA astronaut Donald Pettit on the show speaking about evidence for a much thicker atmosphere during the time of the dinosaurs, which, of course, if the trend is persisting backward, you end up with quite a thick atmosphere at some point in the deep Earth's history. So today, Dr. Marvin Herndon is joining us to speak about what the implications are for a much larger, thicker atmosphere on the decompression of the surface of the Earth. Dr. Herndon also has extensive scientific ideas about the production of the Earth's magnetic field,
which are laid out neatly in his book, Paradigm Shifts.
Really good book. Highly recommend it. And then he also has some cool ideas about nucleosynthesis, where all of the elements are coming from, and has some ideas that are new. They're new to me and hopefully new to you. So anyways, welcome to the show, Dr. Herndon. My first question for you is, where are we coming from in geosciences? What's sort of the history of our understanding the deep interior of the Earth, something we can't really touch very well? And what's the present landscape, and how do you see things differently? This is a big open-ended question, but I want to start deep in the past and figure out what was known when you got to the field.
Well, I think that what's important is to know what is not known. That's far more important than knowing what is known. But let's talk about the historical development, about what we knew a long time ago about the Earth.
Please.
The ancient Greeks were able to use geometry to find the diameter of the Earth. Isaac Newton was able to show that the Earth was about 5 times more dense than the planet Saturn. But he wasn't able to calculate the mass of the Earth because the universal gravitational constant had not yet been measured. In 1798, Lord Cavendish made some incredible measurements using a torsion balance, and he was able to calculate the density of the Earth quite accurately, even compared to modern standards. I think he came with an average density of about 5.5. Now, in 1897.
Hold on 1 second. Are there units for that average density?
Oh, yeah, the grams per cubic centimeter.
Excellent.
Yes,
that's fine. I was like 5.1 of what?
Well,
I'm going to be thinking
what I
about
should
that.
really say is about 5.5 times the density of water.
Excellent.
That gets rid of any problems there of units. Anyway, in 1897, Emil Wiechert, a German, got to thinking about that density and realized that density is greater than the density of rocks. Now, Wiechert had seen meteorites in museums that consisted entirely of iron or nickel-iron alloy. And he had seen meteorites, some of which contained both the iron metal and the silicate material, rocky type material. So he had the idea that the Earth had a core like the iron metal of meteorites. And he made some calculations to show this was reasonable. Well, in 1906, Richard Oldham was making seismological measurements, earthquake measurements about the Earth. And he realized that when earthquake waves went deep into the Earth, they speeded up. They got faster. And to him, that said that there must be a different material in the Earth. And he realized that this was in fact the core of the Earth. Now, it's important to note that when earthquake, well, let's go back a different story. You probably, maybe as a child, stood on the edge of a swimming pool, tossed a coin in, and then dove for it. And it wasn't where you thought it was. Well, that's because light changes direction as it enters a different substance at an angle. Well, earthquake waves do the same thing. When they go from one material into another at an angle, they change speed and they change direction. This is crucial concept. But at any rate, this Oldham realized that the Earth had a core. And by 1930 or so, the seismologists had realized that it was a liquid. It was a liquid because it could only waves, earthquake waves that vibrated in a forward direction could go through it, not the ones that vibrated laterally. It's the same situation as you can tear a piece of paper, but you can't tear a liquid. So what the seismologists knew by 1930, they had gotten pretty accurate about the dimension of the Earth's core, and they had realized that it was liquid. Now, to think about this in terms you can appreciate, if you were to travel to the center of the Earth, basically you would get about halfway down and you'd realize that this core. And so this was the understanding in 1930, that there was one big, massive fluid core thought to be iron metal or nickel iron metal, like the meteorites. And at the very surface, a very thin layer, the crust, that was discovered in 1909 by Mohorovičić, a Serbian scientist. Well, in the 1930s, early 1930s, there was a mystery arose. When the earthquake waves entered the core at an angle, they're bent. And so the seismologists realized that there would be an area on the surface of the Earth on the opposite side from where the earthquake waves started, that there would be a shadow zone. In other words, you would not be able to detect earthquake waves in that shadow zone because they would be bent by the core. But lo and behold, they were discovered in the shadow zone. And this was a big mystery. How did this happen? Then along came Inge Leman, a Danish seismologist who figured out what it was. And what she did is she reasoned this. She imagined that there was a solid object inside of the fluid core that would reflect earthquake waves into the shadow zone. And she was able to deduce the size of this object. And her arguments were so compelling that seismologists accepted this idea that could only be proven in 1960. But her arguments were so compelling.
What do you mean? What do you mean proven?
Well, how could you tell that there's an object at the center of the Earth? You see the reflection, and that seemed to make sense. But how they actually proved it was in 1960, there was a very, very large earthquake in Chile. And what it did is it caused the Earth to ring like a bell for 2 weeks. Imagine this inner core just vibrating and ringing like a bell. And of course, that modulated all the earthquake waves. And so that was the proof. Also, atomic detonations caused the earth to ring like a bell, and that's further proof. But her arguments, her reasoning was so precise.
Sorry, hold on 1 second before we move on. Is the idea of it ringing like a bell being proof because only a solid object would resonate in that way?
Well, because if there was no inner core, it would not be like a bell. Okay, you think of a spherical bell. You've got the silicate part of the earth. Then you've got the fluid. And with the inner core, then the inner core would vibrate. And that would resonate throughout. And that would modulate any earthquake waves that were going through. It would be modulated with this resonance.
And liquid wouldn't be able to vibrate like that?
No,
I see.
Not in the same way. And they're very sophisticated mathematical techniques for showing that it's not a trivial exercise.
Mm-hmm.
I have one question before we go too far into past this in the history. What did people make of lava? And, if they thought that the liquid was only in the center, what's up with all this liquid that they were finding on the surface periodically?
Oh, the surface is nothing compared to the Earth. I mean, the Earth is huge. I mean, you're talking about an object that's 25,000 miles in diameter. I mean, in circumference. About
I guess my question is
miles to the center of the Earth. About 4,000 miles to the.
Did they think that it was leaking from the center, or?
No. This is far removed. Forget what's at the surface right now.
I was just wondering what the people thought back then when they were hypothesizing that the center was liquid.
Well, I think that the only people see the difference is that back at that time, in the first half of the 20th century, there wasn't much government support for science, almost none. And so you couldn't go into science expecting to make a comfortable living.
Definitely.
And so only very dedicated and very highly educated and intelligent people did that. And there was a lot of competition for that. I mean, it was not easy to get into science at that time. And so the people who were conversant in that area were generally, they knew that there was a whole different world down there as opposed to up at the surface. Well, let me get back to the Earth.
Yep.
So now you have a new picture of the Earth. You've got, if you were to go into the Earth from the surface, halfway down you'd get to a fluid iron alloy core. And as you further progress near the center, you'd find an object that's slightly smaller than the moon and about 3 times as massive. This is the inner core. And so this presented an entirely new problem for the geoscientists. You can determine the physical parts of the Earth through seismic measurements or moment of inertia calculations. But to understand the chemical composition, you have to rely on meteorites. Meteorites were formed at the same time the solar system formed. And so they give us bits of debris that tell you what different substances were able to form. But it's not a simple picture because there are lots of different types of meteorites. And so the problem of understanding, well, what is the inner core? This was solved, if I can use quotation marks, it was solved by Francis Birch in 1940. And here's the rationale. Birch and many others thought that the Earth resembled one of the very common ordinary chondrites, one of the most abundant meteorites to fall to Earth. And in those meteorites, nickel is always alloyed with iron. And if you were to take all of the elements heavier than nickel and put them together, they would not make a mass big enough to be the inner core. So Birch explained the inner core as iron that was starting to crystallize from the melt. Think of an ice cube in a glass of ice water. Now, Birch could not give a reason why the inner core has the size that it has, because if it were crystallizing from a melt, it could be very small, it could be very large. But this was the idea, and there was nothing else in the literature that would lead you to think otherwise.
And so basically what you're saying is that if you took one of these ordinary meteorites and you were to melt it down and you were to look at the proportion of the various elements, the amount of nickel, because the core at this point, do people know what it's made out of? They think that it's nickel iron?
Let me follow up with the way you started.
Sure.
If you were to take an ordinary chondrite and melt it in a gravitational field, the iron sulfide would meld with the iron metal or the nickel iron metal, and it would settle to the bottom. Mm. And that's what basically they envisioned the Earth to be.
And you're saying that doesn't work out because the amount of nickel iron that you have for a meteorite of a given size is too small to account for the size of the inner core?
No. What I'm saying is that the iron and nickel would all be dissolved with the sulfur. And if you imagine that all the other elements might want to be the inner core, they couldn't be because there's not enough of them. Elements heavier than nickel, heavier than iron. There's not enough of them. So what makes the inner core? Well, this is what Francis Birch thought. He said, okay, it must be iron metal that's crystallizing from the melt. Okay, now this idea persisted for 40 years. Now, at the time, in all fairness to Francis Birch, he couldn't have known any different because the discoveries that were needed to understand something different weren't made until the 1960s. One of the discoveries in the 1960s was that silicon is dissolved in the iron of certain meteorites. Another discovery that was made in the 1960s was a compound in some meteorites of nickel and silicon, nickel silicide. Now, in the 1970s, I was working trying to understand how a group of meteorites that Francis Birch had ignored, how they formed. They're called Enstatite chondrites, and they formed under very oxygen-starved conditions. So much so that some of the elements that normally would combine with oxygen occur in part in the alloy. Silicon, for example. Calcium, for example, uranium, for example, magnesium, for example, occur in part in the core, not just in the rocky part. And I was looking at these. What I was doing was I was studying very intently the microphotographs or photomicrographs that people, for example, Paul Ramdor, a very famous, very top-notch petrologist, had published in trying to look at the minerals and understand them through his eyes and through others' eyes. And when I started thinking about the nickel silicide, I realized that, hey, with the abundance of nickel relative to iron being about 5% or so, 6%, if silicon were in the core, then there's reason to think that nickel silicide would precipitate. The silicon would take the nickel out of solution, and it would be more dense because of the other alloyed elements, and it would end up at the center of the Earth. So what I did was I derived this logically, and I wrote a paper. And the paper had a very simple name or title. Anyway, the abstract basically said, from observations of nature, the suggestion is made that the inner core of the Earth consists not of nickel iron metal, but of nickel silicide. So I took the paper, first showed it to Harold Urey. And as he was reading it, a smile came on his face. And he said, yes, yes. And then he offered to communicate that to the Proceedings of the Royal Society of London.
And just so you guys know, Urey is the Urey of
the Miller-Urey
experiment. Excuse me.
Yes, he was a Nobel laureate. He was one of the group of scientists that included Albert Einstein.
Never heard of him.
He was head of the isotope separation for the Manhattan Project, and he also conceived of the idea of oxygen isotope paleothermometry, which is widely used now.
Mm-hmm.
That's a big word.
This was a giant among giants.
Let me ask you this. So does this new composition does it solve a problem that was standing?
Oh, let me answer that with a little bit more discussion. No,
okay, I'm just trying to understand. Like, I sense that you were saying that it solved the problem of how the iron precipitated out.
Well, this is the beginning. This was a fundamentally new idea. I mean, for 40 years, people had been thinking that the inner core was partially crystallized nickel iron metal. And the whole understanding of a lot about the Earth was based on that. And so along I came and said, well, if the Earth is like the inside of the Earth's like an Enstatite chondrite, then in other words, if silicon's in the metal, the silicon would take the nickel out and it would make an inner core precisely the mass that's observed for the inner core. And that was published in the Proceedings of the Royal Society of London.
Sorry, 1 second. I'm sorry, I have a question. How uniform is the composition of various Enstatite chondrites? So if you
there's a lot of difference, but let me get to that.
Okay.
Because these are all things that will be answered. So anyway, I had chosen to make the calculations an Enstatite chondrite called the abee meteorite, where number one, there was the most data available, and number two, it seemed to be the most primitive, in the sense of being unaltered. So anyway, while I was waiting for this paper to be published, I had sent a copy of it to Inghe Leman, the lady who discovered the inner core of the Earth. And I got back a highly complimentary letter from the lady. She said, "I admire the precision of your reasoning based upon available data, and I commend you on the highly important result you obtained." Now, this is from a lady who reasoned the existence of the inner core, and I reasoned the composition of the inner core. And I thought while I was waiting that when it was published, there would be discussion and debate, as it should be. And I worried that people who had well-funded labs would just take the idea and run with it and sort of leave me in the dust. Well, when it was published, it was as if it wasn't published, if it hadn't been published. There was silence. No one debated it. No one acknowledged it. In fact, the very few people that acknowledged it in papers, I learned, were told to do that by reviewers of their papers. It was as if there was an organizational silence about this, which is not science at all. Now, there's one other aspect of it.
Was your finding inconvenience, or what sort of paradigm did it overturn? Was there other science built upon that, the idea that it was iron nickel?
What's the motivation here?
Answer that question. One sec. It was not only scientists that were silent about it, but this was supported by my NASA grant. And my NASA grant was not renewed for no good reason at all. I had crossed the line.
I'm sure they thought it was a good reason.
Yeah. Well, no, I had crossed the line.
What was who drew the line?
Yeah,
though?
but why?
What's this line?
Yeah, what was the other science that was potentially
being overthrown?
Here's what happened in the scientific community. World War II came along, and that was the beginning of support for science. And then, just as World War II was beginning to wind down, President Roosevelt, asked his science advisor to formulate a means to support civilian science after the war was over. And he did. It was a book called Science, the Endless Frontier. And this was the basis for the establishment of the National Science Foundation in 1951. 1951, the National Science Foundation wrote the rules for how to administer grants for support of civilian science. And the rules did not make sense, not from a human nature standpoint, not from a business standpoint.
What were the rules?
For example, scientists were called upon to review other scientists' proposals for funding, so-called peer review. Well, they were also given a cloak of anonymity. In other words, people that were reviewing, say, my proposal, which would be mostly my competitors, would then be able to make whatever comments they wanted to make without me knowing who they were.
So conflicts of interest are sort of built into the peer review system.
Oh, it is. The conflicts of interest are part of science, deeply embedded in post-World War II science. And NASA is even worse than that. They had a committee of people from institutions that received their grants that would rank proposals so that the bureaucrats could decide which ones to fund.
But wouldn't NASA deeply, being a technological engineering institution fundamentally, wouldn't they really need to know the best theories for what's happening in nature? Like, aren't they somehow motivated
But
to?
this is a corruption, right? Because what's
Well,
happening is that the scientists that are within the institution that have a stake that their theories are taken to be the ones that actually describe the Earth are walking around and being like, well, these theories are the ones that you should fund, and these theories you shouldn't fund.
So it's like a decay of the institution.
Yeah, like NASA's like, we're going to get our experts to evaluate these so that we have the best
I see.
proposals, but the experts are fallible humans that want their proposals to be the ones that are funded.
I wouldn't say just fallible humans. They're largely academically corrupt. I mean, science is all about telling the truth. I mean, when a new discovery is made, it's the obligation of the scientific community to try to refute that. I mean, that's how you determine whether there's a validity in a new idea. You try to refute it. And if you can't refute it, then you are obligated to cite it in the literature so that other people can be aware of it. This is ethical science. This is real science. This is the kind of science that was pervasive in the first half of the 20th century. But it exists no longer. So what happened, you'd like to know some of the implications. Let me give you
what was the threat?
Preview. Yeah. Let me give you a preview. First of all, the problems are the things that have evolved with the idea of the inner core being iron metal in the process of crystallizing. Well, the first thing is, if that were true, then if you measured the temperature at the boundary of the core, at the respective pressure, that would be the temperature that iron would crystallize. So you could just compare the temperature at the pressure and know what the temperature is. So all of the ideas about the temperature at the inside of the Earth have been based upon that, and people are still making estimates based upon that. And I could refer
and that
you
temperature. How does that temperature matter? That affects the ability of new elements to form and everything, or?
Well, no, it's just one of the many considerations. But the whole idea of what is inside of the Earth is being based upon this 1940s idea. And this is permeated. This is permeated through time, and it is still. There was a paper published this year in Science, in Nature. Nature is the widest read publication in science. And the idea was that there are some other elements in the iron of the inner core that give it some different properties.
I saw
and
that.
This paper mentions a number of other problems with the inner core being iron metal. But a long time has elapsed since 1979, and that work I published is totally ignored. The people are still functioning on the basis of this idea, this 1940s idea. So let me tell you.
Did this Nature paper that was talking about the inconsistencies with the current model of the core, did they cite your work?
No, that's the point to be made. My work is non-cited. It's as if you have a cartel.
Do you think that maybe they just couldn't find it? I mean, like, if it hasn't been...
Look, when I was a young scientist, I used to go to the library and spend days searching the literature by hand, okay? Now you have computers. You can do a literature search in 5 minutes.
That's true, but they're algorithmically ranked in some way. Like if you do a literature search, things come up and it's not always easy to find papers that are from the 70s.
Well, the other thing you need to do, and this is important about science.
I'll also hold on one second before, which I do want to know what's important about science. I want to make another point that the amount of time that people have to devote to literature searches is nothing like what it was even 20, 30 years ago. Because this is viewed as, especially at these top schools, especially in laboratories that are publishing nature papers, I have never really seen a culture where people have a lot of time to do a ton of very careful overview of the old literature.
Well, it's nice
Would
that
you
you
agree?
defend them so.
I got lucky in grad school, so I had a great lab.
It's nice that you
You're probably
defend them, but when you're doing science, what you want to do is to find the truth,
Sure.
no matter how long it takes. Now, it turns out that one of those authors on this paper I referred to was at the geophysical lab in Washington. And he ultimately became a member of the National Academy of Sciences. And I sat down and I talked to him about this. Okay, so you can't say that he never was exposed to it or he didn't have time.
Yeah,
mean,
like face-to-face discussion of an idea kind of enters it into the record.
So
No,
are these?
it's just no. Here's let's go back to what the problems that arose from failure to understand. Number one, the steps in the scientific literature, and number two, the failure to question existing ideas. See, if you want to make discoveries, one of the most important things to do is to ask the question. This is a catchphrase from the 1980s. It was in the movie Terminator, for example. What's wrong with this picture? You ask that question and you begin to find where you can make important discoveries. Now, let me go back and tell you what happened as a result of the inner core concept.
Please.
Okay, and then I'll tell you what did not take place in the scientific community. Okay, my understanding was that if there was silicon, then it would precipitate nickel and make an inner core of exactly the mass that's observed. But that wasn't enough. The next logical step is, okay, if the inner core was nickel silicide, it must mean that the core of the Earth is like the alloy portion of an Enstatite chondrite. In other words, having silicon and whatever. Now, if that is true, then it must mean that the core is surrounded by a silicate shell like the silicate of the Enstatite chondrite. So what I did was, using only mass ratios, I calculated mass ratios of the inside of the Earth and mass ratios of the analytical data of the minerals in an Enstatite chondrite. And what I did was I calculated where that boundary at the top of the silicate shell should lie. And it turns out that it was within 1 or 2% of a major seismic discontinuity that separates the lower mantle from the upper mantle. The upper mantle has several discontinuities in it. It's a little more complicated. So that basically said that the inner 82% of the Earth is like an Enstatite chondrite. Now, what I did then, well, let me go back a little bit further. Francis Birch, in 1940, had the idea of the iron crystallizing. In 1952, he published a paper in which he describes in great detail how important meteorites are. But he laments there's no way to know which meteorite is like the Earth.
Mm-hmm.
Well, I figured that out, how to do that. And you do it by mass ratios. The ratios of mass of the components of the meteorite can be compared to corresponding parts, mass ratios of the inside of the Earth. And that's
how are you
what
getting the mass ratio of the inside of the Earth? You're just looking at magma?
No, you're looking at the ratio, for example, of the lower mantle to the core of the Earth.
I see.
Okay, that must be comparable to the silicate to alloy ratio of a certain meteorite. Now, it turns out that only the Enstatite chondrites have the appropriate amount of iron to make a mass as big as the Earth's core, not the ordinary chondrites. So this is one more piece of evidence. But then I found that the abee meteorite is almost precisely identical to the mass ratios of the inside of the Earth. And so this is basically identifying in a fundamental way which meteorite you can compare to the inner 82% of the Earth.
And so for an abee meteorite, you have this meteorite that you look at and you're like, these mass ratios are perfectly corresponding to what we see in terms of these transition zones inside of the Earth. But then if you take any abee meteorite, does it have the exact same composition?
Oh,
or do you have to look at this?
What I'm saying,
sorry,
wait, let me correct something here. The abee meteorite
is a specific type of Enstatite.
One meteorite.
I realize that
you're talking about are Enstatite chondrites, and no, they all wouldn't be the same.
Okay.
The abee is an Enstatite.
Yes.
But
sorry
it
about that.
compares very nicely. So one of the things that I was very interested in, and I think I mentioned this in a 1982 publication of how important it would be, is to ascertain where the uranium is in the abee meteorite. Well, it's almost serendipity. In 1982, Mike Morrell and his colleague at Caltech actually measured that. And they found that most of the uranium, if not all of the uranium in the Enstatite chondrite, was contained in minerals that would be in the correspond to the core of the Earth. Now, that's interesting because previously people had thought, well, uranium is one of those elements that loves to be combined with oxygen. So people thought it must be in the upper part of the Earth where the silicates are. But no, it's in the core of the Earth. Now, uranium is the most dense substance. See, the pressures involved. Density depends almost entirely upon atomic mass and atomic number. So uranium, being essentially the most dense substance, would end up at the center of the Earth.
Makes sense.
And but
that changes everything, right? If we have uranium at the center of the Earth,
it changes everything. And I'll tell you why it changes everything. Because as I published in 1993, I used Fermi's nuclear reactor theory to demonstrate the feasibility of a mass of uranium at the center of the Earth functioning as a nuclear fission reactor. Now, when I did that and I published that, my first thought was, well, it's the energy source for the Earth's magnetic field. Okay? The Earth's magnetic field has been thought to come about because of convection motions in the Earth's fluid core.
Mm-hmm.
This was an idea in 1939 by Walter L. Sasser.
And the idea here is that the charged material that's on the inside of the Earth, as it moves, creates the magnetic fields because there's an electric current inside the convection current?
Well, the idea is because the fluid core was thought to be electrically conducting, that this motion from convection, altered by the rotation of the Earth, had the consequence of forming a dynamo action, like a magnetic generator, magnetic amplifier, actually a magnetic amplifier. And so the assumption was that some little magnetic field from somewhere would be magnified. And this is the idea that has persisted for the Earth's generation of the Earth's magnetic field. Well, in science, it's very difficult to prove something is, in fact, correct. It's very easy to prove something is incorrect. So what the problem is that all too often scientists don't look in detail at the underlying science. Think about convection in the Earth's fluid core. Now, you can envision convection. If you imagine a pot of water on a stove top, put some tea leaves or celery seeds in it, and before it starts to boil, you see the circulation top to bottom, top to bottom. That is convection. It's an easy concept to envision. And people do all sorts of things to try to deal with this mathematically. But no one seems to have given a lot of thought to convection in the Earth's core. I mean, the rationale is, okay, you've got a magnetic field, therefore you must have convection. No, not necessarily. Well, let's ask what is necessary for convection in the Earth's fluid core. Well, imagine you provide a little bit of heat at the base of the core. It becomes slightly less dense. But is that difference in density enough to make the Earth's core top heavy? So the top falls down and the bottom goes up.
This is like a lava lamp, right? Which is an apt example.
You see, but the thing is, you've got the weight of the Earth on top of that. So the density of the Earth's core is 23% greater at the bottom than it is at the top. So a little bit of heating, or even a lot of heating, is not going to decrease the density by more than maybe 1% at most.
And so you're saying that it's basically like, if I'm still thinking about the example of the lava lamp, that the distance between the reservoir at the bottom and where it cools and starts to fall is so great that the very, very bottom of it is the difference in density is such that even if you heat it, it still wouldn't float up to the top, basically, and then fall back. Or it might float up to the top, but wouldn't be able to fall back down.
The thing, what convection is all about is it creates an instability, a gravitational instability, where you have matter at the top being top heavy that wants to fall down and be displaced by the matter that is not so heavy or dense. Now, they can't have that in the core because the density due to the compression.
Mm-hmm.
So you don't really have compression in a lava lamp. You don't have much gravity. But at the base of the Earth's core,
But if the lava lamp was 4,000, what is it? 4,000 kilometers is the radius.
Yes.
Like if you had a 4,000 kilometer lava lamp, then the stuff
Yeah.
at the bottom would just be so dense that it wouldn't be able
It
to.
wouldn't do that. Now, so number one, you can say that thermal convection is physically impossible in the Earth's core. But if that's not enough, I'll give you a second reason. For convection to be maintained, and there are periods of time when the Earth's magnetic field has been stable for 1 million years. For sustained convection, the heat from the bottom that is brought to the top has to be removed very efficiently, very quickly.
Mm.
Well, the core is surrounded by a blanket of rock that has less thermal conductivity, less heat capacity, less ability to remove heat. So even if you had convection, it wouldn't last very long because you would have the difference in temperature would minimize, and convection by definition requires a difference in temperature between the top and the bottom. So that's two ideas that were totally ignored by the scientific community. Well, I began to say, well, you have a magnetic field. And so if Enstatite is right about a convection-driven dynamo, that convection-driven dynamo isn't in the Earth's fluid core, it is in the georeactor. It is involved in the nuclear subcore. And this now makes sense. And it makes sense for more than one way, because what you've got, imagine.
This is the uranium heavy part, the deepest part.
Yes, this is the uranium, because what you have at the center of the Earth, you have uranium, but you also have above the uranium a shell that is fission products, for example, decay products, and any impurities. Now, decay products are reactor poisons, but they are less dense. You know, you split a uranium atom in half, basically, so you're making much less dense products that would leave the reactor area. And you have then a situation where you've got heat at the bottom, you have a means to move that heat in this microgravity environment up to the base of the inner core, which is a big heat sink surrounded by an even bigger heat sink to take the heat away. And you have a means there for self-regulation, because if you're thinking about uranium precipitating out, if too much uranium gets precipitated out, it fissions and makes too much heat that disrupts this whole thing. And so in this microgravity environment, you basically reach a steady state where the amount of heat is just enough to keep some of the uranium in solution in this subshell, and only allow the amount to precipitate out that leads to a balance.
So the part that's in the subshell is protected from fissioning?
Yeah, the subshell. Yeah, the subshell is full of reactor poisons that absorb neutrons.
I see. So it can't.
If you
need to have these wild neutrons flying around in order to have fission, basically.
Well, and see, here's the thing: if you didn't have a way to separate the fission products, the reactor might operate for a time, but the fission products would eventually steal the neutrons because they have large absorption cross sections, and it would eventually shut down. But because the reactor poisons are half the mass and half the atomic number of uranium, they diffuse upward away from the subcore. So this whole thing makes a lot of sense. This provides a means for generating the Earth's magnetic field. Where
let's go back to that for a second.
Yeah, because I was going to ask about reversals or times where it seems like there's some kind of attenuation of the magnetic field.
You're reading my mind. I was just going to explain that to you.
Can we just go over the field generation one more time? So you imagine a dynamo, but it's smaller and it's more central.
Yes, and it also has a lot of radioactive material in there, which is always producing charges and things like that.
And the reason the dynamo works on the smaller scale is because the difference in density between the central part and the outer part is smaller than it is in the dynamics of the mantle?
Yeah, because here's the thing, the georeactor is 1/10 millionth the mass of the fluid core.
Got it.
So you're talking about not very much difference in density.
Got it. So it's like it's a micro region that because it's so small has dynamics that we're thought to apply to the rest of the core, but in reality can only work out. So you basically took these dynamics that somebody thought was already happening inside of the Earth, and you were like, that doesn't make sense because of this and this reason, but it could be happening on the smaller scale, which is at the center. And given this composition.
And there's another big advantage to that. The radioactivity is complicated because things are decaying and they're changing. And so what this system of self-balancing is, it maintains a generation of heat that's stable over time. Because even if the concentrations change, they adjust themselves, okay? So what that means is that unless something happens, the Earth's magnetic field should be constant. And it is constant for periods in the geologic past, they call them supercrons, where it might be constant for as much as 1 million years or more. But we know about the times when the Earth's magnetic field changes. It reverses direction, or it shuts down and starts up at the same direction. That's okay. Now, there are 2 reasons that I've published as to why this can happen. And they both involve upsetting the convection in the georeactor. And one reason is if trauma occurs to the Earth, such as an asteroid, a big meteorite impact, or a sudden splitting of the continents, that can disrupt this convection in this little, maybe 10-mile diameter georeactor. And then the field would shut down, and it would then, when it reestablishes itself, either in the same direction or the reverse direction. Okay, so trauma to the surface is one way of disrupting the magnetic field. The other is a change in the flux from the sun. Now, let me explain. If you have a transformer and you put the output of the transformer, you connect a meter, a galvanometer, a voltmeter, and you connect a battery to the other side of the transformer, what happens? Well, the moment you connect it, you'll see a meter will swing over one way, just for a moment, and then it'll be nothing. And then when you disconnect it, it'll swing over the other way, but just a moment. Electrical current can be induced through the medium of the magnetic field, but only through changes. Okay, so if the flux from the sun were constantly impacting the Earth's magnetic field, there would be no induced current induced into the georeactor. But if there's a sudden burst of energy from the sun, some of that energy will be induced into the georeactor that could disrupt the convection. Or likewise, if all of a sudden there was a major sharp decrease, that would do the same thing.
Mm-hmm.
And so in the change in the flux from the sun, the charged particles from the sun could disrupt the convection, which there's another parallel to that. You talk about, or people talk about using nuclear weapons to cause electromagnetic pulse for military purposes. The worst case, that might induce enough change in the georeactor to upset the convection and bring on a failure, momentary or temporary failure of the magnetic field.
Oh no.
Yeah, let's add that to the pile of dystopian horrors that await us.
Well, it is true, and this is I published that too, but these things are ignored by the science community.
Yeah, can let's maybe go back to this idea of what this upset, like why wouldn't people be interested in these ideas? Like let's assume that there is. Okay. Is there some theory that is predominant and popular that is championed by somebody who
no,
has?
Let me tell you something that is more human nature.
All right.
That is not science. People who want to be authorities, to have the aura of authority, they want to be able to be the ones who are controlling what people believe about science. Now, these are not real scientists. Real scientists are after the truth. Okay? But there are a lot of people who are not after the truth. And I think you see it's coming. See, I've been knowing about this now for something like almost 45 years because I've lived this in the scientific community. But in the last couple of years, it is becoming increasingly apparent to many, many people that we are not always being told the truth through our mainstream media, through our elected government officials. And this is
well, that's because institutions aren't able to really focus on truth. I think that institutions are really, by design, only able to focus on the mission of the institution.
Or the careers of institution runners.
And that's...
Yeah, but but see, that's the problem is they're turning out scientific frauds, shams, people who, number one, may not even understand what science is all about.
Well, that's because of how they're trained for the most part, where
but that's not excusable. They're being trained and they're deceiving the public. And that's wrong.
They're being trained to get grants and make technology, basically.
Yeah, like I don't think that there's very much science being done in the academy, period. The academy has become very industrialized. Like I don't think it's a place of science for the most part.
No, by science we mean understanding nature.
It goes far beyond this. Because the real problem began with the National Science Foundation in 1951. The problem is that scientists who need to have support for their work, which means they need to get the support or they will be out of work, their proposals and their papers must be reviewed by their peers that should be their competitors, who are their competitors. Now, scientists aren't stupid. Dishonest as hell, but not stupid. If you're a scientist and you realize, hey, if I cite Herndon's work, then somebody might get at me. Or if I criticize somebody that might be reviewing a proposal, or criticize something that the government institution has supported, then I might be out of the proposal, won't be funded, and I might be out of a job because universities expect their faculty to bring in money.
Yeah.
Can you imagine an alternative structure that would work?
Yeah, like how do you get money to people who are doing science in a way that's fair?
Well, it's
Is it
I think there are probably ways to do this, but they're not the ways that would work right now.
what do you mean?
Yeah, like what do you? I'd love to hear some ideas because this is something we talk about all the time. Like we totally agree with you that there's an institutional decay set up when you bring careers into science because you can't possibly be objective 100% if you're trying to keep food on the table, and that means having something exciting that's popular with the consensus to talk about. But what do we do an alternative? Like how do people do science who aren't already billionaires, basically? Because back in the 1500s when science started, it was only the gazillionaires that were able to do science, like people who were rich already, basically.
Right.
And today, nobody's rich except for like a few people that I probably wouldn't want doing science anyways. So how do we get money to do science? I wonder if
Even if
you have any
things-
insight.
Well, in the first instance, let's talk for a moment about publication, which is now so corrupted either by editors who make decisions who aren't really scientists, or by scientists who want to keep the competition out. The National Science Foundation came up with a really good idea back in 1995. And that was the establishment of the formulation of an author self-posting archive. And they funded this to be done at Los Alamos. But they did not have the supervision and ultimately did something that was just dirt dumb. While at Los Alamos, already, when this author self-posting archive began, which went through a lot of different names, there were allegations that people were being blacklisted. Okay, the idea of the author self-posting archive, which began for physics, was because physicists' papers were being delayed for 2 years or more and often not being published because they're competitors. So the idea was the scientists could post a preprint and it would immediately be distributed to other scientists. And then they could go to publish it or whatever they wanted. The scientists would have this information. It's a great idea. But even in the beginning, there were allegations that even while at Los Alamos, that the people involved in that project were blocking people, blacklisting people.
Somebody's got to administer it.
No, actually not.
Well, somebody's blocking somebody. I guess that's what I'm trying to say.
Yeah.
Somebody's running the server.
Well, let me go ahead and explain. So anyway, around about the year 2000, the people who established that got involved with the administration of Cornell University, and Cornell University submitted a proposal for just under $1 million that would basically allow them to take over. I mean, they get the money for taking over the archive from Los Alamos and administering it at Cornell. And the people at Los Alamos then went to Cornell. And NSF paid about $1 million, almost $1 million to Cornell to allow this to happen. Well, it got much worse at Cornell. It became institutionally corrupted. And I was, it's a computer that does things until somebody singles you out and lets either the computer know or the administration or whatever. Then it used to be that I was able to post in a lot of different areas. But what happened was that I became blacklisted. In other words, I would submit and I would try to post an article. It might not post at all, or more likely it would be posted under the category of general physics, where no one would see it at all. And they had so-called moderators that would recommend and so forth. But this was, and there were numbers of people who were blacklisted, and one Nobel laureate was as well.
And this is just because the people who were moderating didn't like the content of the papers? Did you ever...
The people who were running the archive would single out people.
And they would basically pass that along to the moderators, and they would be like,
or
anybody...
It would be plugged, my guess is it would be part of the program, so that when my submission came up, it would go to some group of voluntary anonymous moderators.
And you assume these are establishment careerist scientists?
Well, see, here's the thing. This is fundamentally wrong and should be illegal, because Cornell University receives great amounts of money in terms of government contracts and government grants. And so the very idea that they would be suppressing or deceiving the scientific community on matters that were related to subjects that they were receiving grants. I mean, this is not good. Now, put that aside for a minute. What should have happened was, instead of transferring that to Cornell, self-interest group, it should have gone to the Library of Congress and been operated without bias. Now, such a situation would be the first step toward giving an equitable, because then it wouldn't depend on your publishing papers in various journals. It would depend on what you yourself published in or posted in that self-posting archive. And it could even be extended to the point that you would be required to provide a full scientific background as to why you're doing what you're doing when you're doing it. And
sure.
What questions are. So I mean that's the first
I have a
step.
question. Just to be clear, we're talking about arxiv, the preprint server that currently is in use, or this is a different archive that doesn't have anything to do with the archive?
No, we're talking about what is called arxiv.org.
Got it. Okay, so we are talking about arxiv, which is basically the physics preprint server.
Yep.
Yeah,
because there's medRxiv now for biology, but physics solved this. I didn't.
And
this is fascinating backstory.
And it's been systematic. Now I complain a lot. No, believe me,
squeaky wheel gets the grease.
There's a reason for this, and one reason is to document.
Sure, yeah.
And so I made numerous complaints to the administration of arxiv, including to two provosts. Provosts have the responsibility of maintaining the operation of a university in a legal framework. I've complained to the administrator. I mean, the provost always sends my complaint back to arxiv, the very people I complain about. And this is the kind of nonsense.
So was it always the case that you needed to have an institutional affiliation to publish on this self-published archive?
I don't know about that. I know that what they do what they set up to do is to allow anyone with a .edu email or a .gov email to post without question. Anyone without that, you would have to get somebody to recommend you.
Got it.
Which I did in several different areas before I was blacklisted. But now it's gotten so that people tell me that they're afraid to recommend people because they're worried that they will be blacklisted.
It's really astounding to me how widespread this phenomenon is, and how, because it's not just limited to archive, right? And I think for a long time people have been very reluctant to accept this idea of some kind of shadowy level organization that controls the quality of information in a certain sphere. But I think that the last 2 years have really opened a lot more people's eyes.
It up. See, I've been aware of this.
We've shifted the Overton window pretty significantly over the course of the last 2 years.
Yeah, because I've been aware of this from the scientific community for, like 40 years. And, and I used to be able, and it's gotten increasingly bad, I used to be able to publish in the Proceedings of the Royal Society of London, in the Proceedings of the National Academy of Sciences, in various places. Now, I've recently, in the past few years, submitted a couple of papers to the National Proceedings of the National Academy of Sciences. And they have a nice way to deal with that. One member of the editorial board will decide that there's not enough interest among the readership for the paper, and they'll reject it on that basis without review. And one of the papers I submitted had to do with the poisons in the atmosphere. So, I mean, this is, which you can't say that there wouldn't be much interest in. People are breathing air that has toxins in it. So it's...
What was the scientific presentation there? I mean, I can imagine one or several, but...
That's the fourth part of the book.
Say that again?
I said, should we head into this part of the book, or what do you think?
No, let's not get into that.
Yeah, we're not quite there yet.
I want to get back to some other things that came about besides just the origin of the Earth's magnetic field.
I want to hear about the crust too.
I should tell you, or maybe your audience might like to know, that even Albert Einstein worked on trying to solve the origin of the Earth's magnetic field, and he was unable to do so, but he considered that one of the 5 most important unsolved problems in physics. Okay, so now, because I got to this because of the inner core, logical progression of understanding. Okay, well, what comes as well is a logical progression of understanding about the behavior of the Earth. You know that 1912, Alfred Wegener published an idea that had been discussed previously, but he added a lot of proof or evidence. The Earth, his idea was that at one point the continents had been joined.
Well, they all fit up together really nicely.
And then had separated. And he had a compelling evidence for this. Well, this idea was ignored for 50 years by the geoscience community.
And the evidence has to do with rock layer similarities across the continents and the way the margins fit together and the distribution of fossils.
In England and North America and fossil deposits in Africa and South America. But the geoscience community ignored that for 50 years. And then, with a little bit of understanding about the what's under the oceans, it became apparent that there was something that was being missed. For example, in World War II, one of the geoscientists was on a captained a troop carrying ship, and he let his echo sounder run continuously, which sounds really stupid because Japanese, they had caught that. But he traverses across the Pacific. He mapped the ocean bottom. And so what he understood from this was that you were getting at the mid-ocean ridges, which, if you look at the Earth as a whole, the mid-ocean ridges are like the stitching on a baseball. They go all the way around the Earth, very much like a baseball stitching. What he found was that as the salt would come out of the mid-ocean ridge volcanoes, and it would flow downhill until it got to a trench, usually near continent margins, where it would fall into the trench. And so he thought, well, the Earth, the mantle must be convecting. You see the fallacy of the reasoning. Comes out, it goes across, it goes down, therefore convection. No, that's not the case. But this is what plate tectonics was based upon. Now,
they needed a mechanism to spread the things, right? They need them to move somehow. So
they need to move it in a circle because they believe the Earth is the same diameter, the same size. And so they needed to have a mechanism for the lava to keep the balance, and they assumed it's convection. And that underlies all of plate tectonics. Well, mantle convection is physically impossible. And the reason is because the mantle is 62% more dense at the bottom than at the top. The same problem we had with the Earth's core. So let's just put that aside and say there's a problem with plate tectonics. And let's go back a ways. Okay. There was another idea in 1930. Ott Hilgenberg had an idea and spent most of his life making physical models and talking about this. His idea was that the continents were joined, but on a smaller Earth. They fit together like pieces of a jigsaw puzzle. And he imagined that the Earth was 1/2 the diameter, or I'm sorry, yeah, the radius of the diameter, 1/2 the present. And they would fit. And then his idea was that subsequently it expanded. Well, he didn't know what could cause that. And in 1982, a very well-known geophysicist wrote in a book, if expansion occurred on that scale at all, a new undiscovered energy source must exist. Because you're talking about lifting against gravity. Enormous amount of energy.
And hold on. I mean, for the fossil layers to be continuous, this expansion has to have happened relatively recently in terms of geologic time.
Oh, you jumped the gun here.
Sorry.
You jumped the gun here because here's the problem. And this is what the problem of Earth expansion theory was. Number one, there was no energy source. Number two, the oceans are no more than 200 million years old, the ocean floors. Is that the right number? 200,000. No, 200,000 years old. Okay.
I want to say that it's 1.8 million. I looked this up recently. I want to say that the ocean floor is 150.
It says very little of the ocean floor is older than 150 million years.
But I always wonder
all
about
right,
the
there you
sampling
go.
of that.
All right, that's true. And the most is like 180. There may be a little piece that may be 200. And so this was a problem that the expansion had to have occurred on a very short time frame, which also didn't make sense. So this leave Earth expansion theory alone, because there are a lot of problems with it. It wasn't a well-developed theory, but the observation of Ott Hilgenberg was very, very significant. And I remember when I first heard that, all of a sudden, a lot of things made sense. So let's go back to the Enstatite chondrites. Okay? We begin at the beginning. Okay? Why were they so oxygen starved? Well, this was a big mystery in the science community back in the 1970s because no one could understand how this could happen. Well, I published a paper with Hansus that explained how it happened. When you talk about material condensing from a primordial gas, in other words, a gas like the outer part of the sun, most substances condense. The condensation is simply based upon pressure. Higher pressure, it's a higher temperature. But oxygen is tied up with hydrogen, major component of that mixture. And so that is a reaction. H2 plus 1/2 O2 equals H2O is independent of pressure. Okay? So that reaction establishes at a given temperature what the state of oxidation is. And so as you go to higher temperatures, you get to a more reduced oxidation state, a more less oxidizing oxidation state.
Because your oxygens are bound up?
Because the oxygen is bound up with hydrogen and the reaction is independent of pressure. So it's fixed. And if you go to higher pressures, you're moving everything else, the condensation temperature up, and you move it up into a more reducing range. And so eventually, the most refractory, the first major substance to condense is iron metal, liquid iron metal. And as opposed to what the science community was thinking, that this was happening at pressures of 1/10,000,000th of an atmosphere. We're talking about pressures above 10 atmospheres. It's an entirely different realm.
How do you get to these kinds of pressures? If you're starting with a gas cloud that's condensing, presumably there's not a lot of pressure in that gas cloud at first.
Well, that depends on the gas cloud. And this is what the community was thinking, that it was very low. The hydrogen pressure was very low. In 1944, a German scientist.
Uh-oh.
No, this was anyway. He used thermodynamic considerations to show what would happen when the Earth formed from high pressures. And he showed that the first condensed would be liquid iron that would rain to the center by gravity, followed by silicates, and followed, if it continued, by the ices and the gases. Well, I knew from the work on the Enstatite chondrite that this was what you would get, is condensing at high temperatures. If you isolated that condensate so it didn't react at lower temperatures, you have the evidence of the high pressures. giving
What's
the
the
state of
proposed
oxidation.
source of that pressure?
Just a gas cloud, a giant gaseous sphere, if you want. The ideas go back, a couple of hundred years to the idea that the solar system formed from as protoplanetary condensation, and
the nebular hypothesis, as it is.
Yeah, and the subsequent was the planetesimal hypothesis, and the science community in the 70s were involved in the planetesimal hypothesis, where you condense the dust, it would then roll up into balls and get bigger into rocks, boulders, then planetesimals, and they'd collide together to make planets that then had to undergo whole Earth melting so that the core would drain down. Okay.
Very quickly too. That whole thing's supposed to happen in a few 100 million years, I think.
Well, this is now. Wait, we're
off topic.
Yeah,
sorry,
we're off topic,
We've had folks on the show who have serious problems with that story. So I just curious. But anyways, it's off topic.
We're going back to the formation of the solar system now, to the time when the Enstatite chondrites formed, however they formed, and the work that predicted the formation of the Earth from a giant gaseous protoplanet. And so I got to thinking about that, because you end up with the fluid core from which things precipitate, the inner core, the things that float to the top of the core. And then if the condensation continued, you would end up with a planet about the mass of Jupiter. You put the Earth back together with all of its primordial components, and you're talking about a planet that is maybe 300 Earth masses, mostly surrounded by gases.
That's a big Earth.
So let's say what would happen there. The sun hasn't ignited yet. Okay, because you have all these ices and gases. The weight of 300 Earth masses is going to compress the solid part to about 2/3 its present diameter. Maybe 70%, maybe 2/3. All this weight. Now, then the sun ignites. Well, the ignition of thermonuclear reactions are not quiet. I
was actually just looking at videos of nuclear reactors coming online, and it is one of the most. Everyone should go look this up, because
beautiful.
It's not only is it beautiful, but you can see how violent it is when it goes from being off to being on.
Send me a link by email if you would.
Yeah, sure.
It's in our latest movie too, by the way, folks.
But anyway, there's a nice Hubble Space Telescope image that I've used in numbers of my publications. It's a binary star system that is pouring out masses of hot gases. I mean, this is the T Tauri phase, and they took 2 pictures of it spaced by 5 years, and so you can make a mark and see the progression in 5 years. Well, if that had happened at the center of the solar system, it would have stripped the gas, certainly from the Earth, all of the matter. And so this is what I've suggested happened. The Earth, the sun ignited, it went through this T Tauri phase and ejected a lot of energy and mass that literally stripped away the gases, leaving behind a compressed solid Earth, maybe about 2/3 the diameter, maybe 70%, something like that. Now, when you compress a substance, it gets hot. Well, that heat was lost. So when you decompress a substance, you have to replace that lost heat of compression. And so you have two energy sources within the Earth. You have the stored energy of protoplanetary compression, and you have the georeactor nuclear fission energy. And so the stored energy of protoplanetary compression is much, much greater, but it can't decompress on its own, because if it decompressed, it would have to cool, and that would impede the decompression. So the georeactor supplies that lost heat of protoplanetary compression, and it allows the Earth to decompress.
Why is it
Now,
not an explosive event?
Pardon?
Why is it not an explosive event? Like if
Because it's not, well, for several reasons. Number one, you're talking about lifting all this huge mass, and you're talking about this little georeactor supplying the heat of the lost heat of compression. It couldn't supply it all at once anyway. Plus, you've got the rocky part surrounded by a hard shell. Now, cracking a hard shell takes a lot more energy than propagating the crack. So as the Earth began to decompress, there would be a lot of stress occurring. And at some points, cracks would occur. And as the Earth decompressed, these cracks two things would happen. Basically, as the Earth decompressed, it had to make more surface area. It does that by making the cracks. Now, the cracks, you have the lava that's being extruded.
And this is at the Mid-Atlantic Ridge.
Yeah, that flows across whatever ocean bottom exists at the moment and falls into a decompression crack, a crack without a heat source. And this is a continuous process of infilling of cracks. Now, one of the things that plate tectonics can't explain is that you have partially infilled cracks in the middle of the ocean. That doesn't make sense to them. But of course, it makes sense in this connection, because as the Earth decompresses, it must make a larger surface area. It makes it by the cracks. Two kinds of cracks: the kinds with heat sources under it that produce lava, and the kinds without heat source that the lava infills. So it gives you the emulation of what you're seeing in the ocean floor presently, with basalt coming up, moving across, and infilling a decompression crack without the circulating mantle compression. But that's only half of the story.
Well, hold on. Before we get to the second half. So would based off of what you just said, which is that there's this flow of the basalt across the surface, because I'm just trying to wrap my head around the age of the ocean floor and the pattern of fossils across the continents. And so if it's expanding and these
you should use
decompressing, of course, sorry. If it's decompressing and the lava is coming out of the rift, and so I can imagine that, it takes about 200 million years or 150 million years to cover the entire bottom of the ocean, and so that's the reason that it looks that old, is because that's just how long it takes to get it covered.
No.
But what about...
No.
Okay.
Imagine that instead of the ocean floor, say from Europe to America, being this wide as it is now, imagine it's only this wide. You see, this is a continuous process as long as you're decompressing. And so we're not talking about in 200 million years. We're talking about whenever this crack formed, it begins to, and it would get bigger over time. And the infilling would raise the diameter as well. in the cracks. So you're talking about infilling over time.
So there's older parts that are just too deep.
But there's
Yeah, that's what I was trying to get at.
so if you were to look below,
like if you were to take a core, let's say that's like a half mile
you
deep.
would see the evidence from previous. Now, that's only half the story.
All right.
The other half of the story, and this is fundamental importance. People have long wondered what makes mountains that are characterized by folding. Okay, the great people, Edward Seuss worried about that. All sorts of geologists in the past have worried about it. The plate tectonics people think it's when mountains collide, when continents collide, which is, I can tell you, is nonsense. But if you think about the Earth when it was smaller, its surface curvature is different. Imagine this. Suppose you take a slice of orange, say across the midsection or something, peel the pulp out, and sit it on top of a melon. It doesn't fit. The curvatures don't match. Well, what I realized is that gravity would cause the curvatures to match. And it would happen in two ways. One way is you'd get stress at the edges that would cause tears. But that can't deal with the whole thing because it would be too many tears. It's not energetically favorable. But it would explain the origin of fjords and submarine canyons. But what happens is you got extra matter in this previous, if you want to call it a previous crust, that has to flatten. And it does so by taking tucks. You take a tuck, fold it over, and it folds over by gravity. And that's how the mountains characterized by folding form. And this is all, this all follows quite logically, because it's not only that the decompression makes the ocean floors, but it also leads to the formation of mountains characterized by folding.
What about those subduction zone things that we always hear about?
Well, that's basically the there are two types of decompression cracks. One where there's a heat source beneath it, such as the mid-oceanic ridges. And the other is where there's no heat source. Now, there's a prominent example of this is around the Pacific. The trenches, the Tonga Trench, the Marianas Trench, these are decompression cracks. And eventually, if enough lava were to fall into them, they would become infilled. Okay, they just haven't been fully infilled, maybe because of the location of the. But that's the evidence that I tend to think of them as primary decompression cracks, the ones with the heat sources, and secondary decompression cracks, the ones that lack heat sources.
What's up with the heat sources? Can you shed some light on that? Why do some places have heat sources and not others?
Well, I will shed some light on one thing that is a consequence of polar decompression dynamics. Imagine decompression occurring deep into the mantle, where the heat was, the lost heat of compression was supplied, and the layer began to decompress. Incidentally, the mantle, is gravitationally layered. Okay, the lighter on the top, heavier on the bottom because of compression and everything. So at the bottom of the mantle, or some point in the mantle, you begin to decompress. Well, that decompression will propagate upward toward lower regions of gravity, less compression, and it will propagate upward until it reaches the rigid crust. And at the rigid crust, you get compression. And when you compress something, it gets hot. And that, I would contend, is the heat source that supplies a lot of the energy at the crust, and as gives you the geothermal gradient. As you know, you go deeper into a mine, like a deep diamond mine, and it gets so hot you have to have air conditioning, and so that's caused by this process. It's another. These things are all missed by the geoscience community because they operate on old ideas. And you know, if you're operating on a false idea or an incorrect idea, like they were doing about the inner core, it's like being in a cul-de-sac. You can't make any progress. It's like stumbling in the dark because you can't discover correct things from incorrect things.
But what do
You
you make
move
of
logically from something that is correct to something that is new and maybe even more correct.
Right. I mean, my question with this still remains the fossil evidence across the continents, because to me that's the most convincing argument for plate tectonics, where if
What?
you because you have these bands of fossils, right? So if you had an overlap of just rock types, I can imagine this perfectly working out because the rock can be as old as it needs to be in order for this to work. But we do have a timeline of the evolution of life on Earth. And so how long ago did this shift happen that it could have already had life on Earth that was rent apart? The records.
Well, this is really a good question, and let me get a little bit go back to the plate tectonics story a little bit. The plate tectonics story is that mountains are formed by collisions of continents. So they envision Pangaea, continent that splits apart and makes what's presently.
Well, we have so many of them. We have Gondwana, we have Rodinia.
Wait,
there's this
wait a second.
Sure.
Let me get here, okay? So then they discover, or somebody discovers, mountain chains that predated the breakup of Pangaea. So they have to invent another supercontinent to collapse, to have collisions that then separates again, and so the whole idea of supercontinent cycles. Well, it's a fictitious supercontinent cycles, because that's nonsense, because number one, there is no energy source in plate tectonics to drive all of this continent mobility.
I always thought that it could have been impacts. So I'm like, I know that there's not, like, as it is right now, it's just convection currents, but I'm like, I imagine a large enough impact could force everything to one side of the planet.
Well, I think that's not the case, because the point being that they depend on these mantle convection currents to move the continents, to bring them pieces together, to suture them, to break them up again. It's nonsense, because there is no energy source to drive mantle convection. In fact, mantle convection is physically impossible. Now, all the things I've talked about are not physically impossible, and they follow quite logically. And in fact, the thing that you will see is that all of the evidence that supports plate tectonics supports polar decompression dynamics. And there's even more.
And that's so often something we see in science, which is really fascinating. We talk to people all the time who have alternative theories, and everybody's pointing out the same evidence, but they have a very different imagination of what is happening with that evidence. And one of the reasons why we're so insistent that science is about examining all of the possible stories and allowing the audience to come to their own conclusion about which one they prefer. Of course, you have to compare it as new evidence arises, and hopefully that can trim away some of the theories, right?
And it also has to fit the known laws of physics, biology, chemistry. Like there's
Right. Anytime a contradiction is discovered, that's a great thing, because then you can trim away one of these possibilities.
Mm-hmm.
Well, this is my way I progress. Is I don't do anything that violates the laws of physics, and moreover, when I seek to understand what people are doing, such as the idea that you have convection in the Earth's fluid core creating the magnetic field, the first question I ask is convection physically possible?
Mm-hmm.
And the answer, of course, is no. And it's I once brought this subject of mantle convection up to a person who works for the government and makes models of these sort of things. And his explanation was that, well, you only have to show how something might be. Now, there was a program on television that was, I can't think quite of the name of it, but it was hosted by Leonard Nimoy. And he would begin with, well, we're going to show one way this might be, but it might not be necessarily the correct way. Well, that's the same kind of reasoning. And that's not legitimate science reasoning. Now, one of the things that people do to make things seem to work is they assume that convection is an adiabatic process. Adiabatic means that there's no exchange of heat, no loss, no gain of heat. Well, that's an artificial construct.
It's very ideal.
And if you look at the mantle, well, you know that the only way you could have adiabatic is if the mantle behaved as an ideal gas. And it doesn't. And you know it doesn't because you have earthquakes in the mantle, some as deep as 600 or 700 kilometers. And earthquakes, as you know, result from a catastrophic release of stress. Well, in an ideal gas or in an adiabatic process, you don't have stress. So you can't.
But the stress that's held is in the crust, not in the mantle, right?
Pardon?
When an earthquake relieves stress, the stress that it relieves is the stress of the crust, not...
Some of them are quite deep, I think is what he's saying.
Well,
I don't know enough about
when
this.
you get down to the crust is only 10 kilometers thick, something like that.
Yeah, but earthquakes originate deeper than 10 kilometers?
Yes, as deep as 600 or 700 kilometers.
I had no idea.
Yeah. So it's the point is the real takeaway on this is that scientists need to do real science and not simply promulgate a storyline. Now, we mentioned NASA earlier.
Not just promulgate a storyline, but a storyline that keeps food on their table. That's the real conflict at heart here, because all we do in science, whether it's the truth or not, it's still a story.
Before we get to NASA and the stories,
they're true stories.
The true story.
Right,
hold
story
on.
Or true or false, it's still a story. Go ahead.
I have not had, to my satisfaction, my question answered about the fossil evidence.
Okay, so you have to be more specific about what we're talking about, fossil evidence.
So, from what I understand, a supporting piece of evidence for plate tectonics is the existence of continuous bands of fossils across these continents that were supposed to have been joined.
Yes, that is correct.
So how does this work under a decompressing Earth model? How do you explain that?
It's the same way, basically. You have a band of fossils, a deposit of fossils, or a deposit of coal, and it splits. Okay, you develop a crack, and the crack becomes wider and wider, and the bottom of the crack gets filled in.
Mm-hmm.
But basically,
But for the crack to get wider, the diameter of the Earth had to have been much smaller when
yes,
it was continuous.
that is what we're talking about.
Of course, but so what I'm trying to get at is the timeline of this decompression. So when these fossil bands are laid down, how big is the Earth relative to how big it is now, relative to how small it was to begin with?
Now this is here's the thing. This is one of the most important things for geoscientists to be working on.
Mm.
And if they're worrying about supercontinent collisions, they're in another world. But we need to establish, and I've said this in publications, you need to establish a timeline of where the splitting occurs and when. And there's reasons for that. One reason is because it relates to other phenomena such as magnetic reversals and to species extinctions and things like that. So it's really important to establish that, and that's not really been adequately established.
So the next level of being able to model decompression theory would be to create a timeline for the dynamics of decompression that accounts for the way that these fossils are distributed.
It's important to establish a timeline based upon the geological evidence,
which includes fossils.
And fossils, this is one way of doing it.
But the fossils were relatively recent, right? Like 200-300 million years ago.
Well, that's kind of what I'm trying to get at.
The splitting of Europe and North America is around 300 million years, or this was the number that Wegener came up with.
Right. And that fits with how you imagine this happening?
Yeah, this is how I don't know what the time frame is. I know that
pretty quick.
A couple of billion years ago, the pressures were great, and occasionally you'd have a little material from the mantle just shoot out of a hole in the crust, leave a funnel-shaped deposit. No, that's the kimberlite deposits where they find diamonds, for example. But there were obviously immense pressures at some point in time, and eventually the Earth split. Didn't split all at once. The cracks propagated. That
must have been a bad day. The day that happened, like all this pressure building up for billions of years, and then the day that it cracks open must have been a rough day on Earth.
There are events that seem to be simultaneous, and they seem to relate to about the 5 periods of major species.
You were just looking that up, yeah.
The extinction periods?
You see that one of them is at 250 million years ago. That was also the time of the basalt floods in Siberia. And another one was 65 million years ago, which was the time of the basalt floods in India. Now,
these are the Deccan traps and the Siberian traps.
Now, both of those, the one thing that I didn't tell you,
which are, sorry, one second, for people to understand, these are areas of the Earth's crust that are covered in mile-thick basalts for an area of hundreds of thousands of square miles. These are absolutely enormous rock deposits that the current model is the fact that there were these dikes that opened in the Earth and lava just poured out of them for millions of years.
Well, there's something that I need to tell you that back in about 1969 or so, scientists started observing helium coming out of the Earth, helium in volcanic material. That the significance is that the helium-3 to helium-4 ratio was higher than it is in the atmosphere, and no one could account for the helium-3. Helium-4 is a byproduct of natural radioactive decay. Alpha particles turn into helium-4, but no one knew a source for helium-3. Well, after much working to get somebody to do something for me, I finally convinced a guy at Oak Ridge National Laboratory to do something. At the time, it was like 30 years. Oak Ridge has developed immensely complicated software to model nuclear reactors, the operation of nuclear reactors, the fission products that are produced, the energy, and so forth, so they could tell if a reactor occurs, what type of reactor it is. And I mean, a lot of money's been spent. And so I convinced Dan Hollenbach to modify their program slightly and run it for the georeactor. And he modified it in two ways. One was to allow it to operate for billions of years, and another was to remove the fission products, because that was happening in the georeactor. And we published the first paper in 2001 in the Proceedings of the National Academy of Sciences. And I published another paper that was with Oak Ridge calculations in 2003, the same place. Now, the interesting thing is, of all the fission products, the helium, the georeactor produced helium in exactly the ratio that's observed coming out of deep earth deposits. Now, no one knew how this could happen, so people made models before this of primordial helium being mixed with just the right amount of helium-4 to give the results, and they published lots of models. Well, that's not the way it is. The helium was produced. And in fact, the helium-3 to helium-4 ratio increases over time as the fuel is being used up in the georeactor. And so the one thing that I can say with a great deal of certainty is that the helium measurements in the Deccan traps and in the Siberian traps all have the high helium-3 to helium-4 ratio that is characteristic of the georeactor. In other words, that heat was involved in that action, and along with the heat came the highly mobile helium. Well, it's also involved in the volcanics at Yellowstone. And as you may realize, Yellowstone is a potential supervolcano. And it's being fueled by the georeactor. So, I mean, these are things that the scientific community should really be being looked at. But instead, they don't. Now, there's another way for evidence of the existence of the georeactor. And this is that the georeactor, like radioactive decay, it produces neutrinos or antineutrinos. Now, there's a little story that's germane to this. In August 2002, my work was the cover story, the feature story of Discover magazine. It was about a nuclear reactor at the center of the Earth. Well, shortly after that, I received a an email from a young lady at Lucent, at Bell Labs. She was going to give a lunchtime seminar and wanted to get some more information about the georeactor from me, and I gladly provided it. Well, one of the attendees at this lunchtime seminar was a person who was very well known for his work with neutrinos and antineutrinos. In fact, in 1998, he had published a paper on measuring uranium in the Earth based on measuring antineutrinos coming out of the Earth. And there was a big project in place, initially a US-Japan consortium. Later, the Italians were involved in another one, and the Russians were considering it. And so he wrote a paper called How to Detect a Nuclear Georeactor at the Center of the Earth.
Before this talk. So by the time that he came to this talk, this lunchtime talk that she was giving, he had
based on that talk.
I see.
He went and did a little bit of her work and submitted a paper to physical review letters. It was rejected. And to physics letters, it was rejected. But it was posted on arxiv, and so the whole community knew about this. And what this basically said was, you can discriminate between antineutrinos that come from radioactive decay and those that come from nuclear fission, because the ones that come from nuclear fission have a higher energy spectrum. And so then when the CAMLAND consortium, which was the US-Japanese consortium, reported the first results from their antineutrino measurements, which weren't really definitive at all. But they mentioned all sorts of conceivable possibilities for antineutrinos, but they failed entirely to mention the georeactor. This was a deliberate. So I, as I mentioned, I do complain. So I wrote to the Japan's Minister for Science and Technology, and the letter began, what should have been cause for celebration is cause for shame. And I basically said that the Japanese, instead of standing up in integrity, had capitulated to American lack of integrity. Well, after that, they always, when the Japanese published subsequent measurements, they always cited the georeactor. But they didn't always do it in a real positive way. But they did. And the last result is that basically they've come up with an estimate of about the Italians came up with an estimate of something like 2.5 terawatts as energy from georeactor. And I think the CAMLAND came up with about 3 or 3.5. And we used in the calculations between 3 and 6 terawatts. So it's really right in the right range. But nevertheless, this was another way of verifying the existence of the georeactor.
I mean, overall, it is a very neatly cohesive story of what could be, and I think that it's a really fantastic example of science in action, because I think that
let's go a little bit back again. Remember, my NASA grant was
yes,
not renewed. Well, after I published the paper on the nuclear reactor at the center of the Earth, and the one about the giant planets, I made a proposal to NASA, and it was reviewed by a committee who were all components of institutions who received money from that pot. And this was ranked of 120 proposals. This was ranked number 120.
Whoa.
Okay, now if NASA, I do not believe, has ever published, funded any paper that cites my work on planetary nuclear reactors, even though I've published numerous works in prestigious journals, and they're completely ignored, and they shouldn't be, because you find, for example, the moon Io that obviously has energetic action going on that can't really be explained by tidal forces and the things NASA explains, but they do not cite the possibility of a nuclear reactor. This tells you that we have in the United States, we have a very large problem, and Europe is not far behind.
I think it's a problem because people don't know what else to do. Like I still haven't. This comes up so often on our podcast, and I'm always trying to brainstorm alternatives to these superstructures we have for funding science, and nobody really has any idea of what to do. Like it's not clear that there is an easy alternative to what we have going right now, despite its corruptions.
There's not, but if you had an honest, if you made the system right now honest, okay, the first thing you would do is to eliminate anonymity. You would eliminate people.
So transparency is critical.
Yes, you would eliminate people going from universities to work with NSF for 3 years as an assistant program manager or whatever. This open revolving door kind of a thing. You'd also have you could also say that if they do not provide the legitimate background, if they fail to provide it, then they are apt to lose their support. You see, they can right now, they can ignore the georeactor. They can ignore the inner core being nickel silicide. But if they do, they should lose their support. I mean, this because what you're doing is you're talking about corruption, because science is all about being honest.
Well, the trick is having somebody to referee that decision who's objective. I think that's the real mess here, is that somebody's going to have to decide whether they included all the relevant background or not.
Well,
who's going to be that decider, you know?
Well, that could also be something of a public record that people could access. And
I think that this is just the side effect of institutions inherently always becoming this corrupted over time. Like, I really think that this is an inherent part of institutional design.
Well, there's another thing one could do. You see, the way it's set up now, the grants are made to the institution, and the scientists serve only as principal investigators.
Right.
Well, no, that's not the way to do it. The grants should be made to the scientists, and if they want to hire the university to provide the overhead support facilities, they can do so, or they could do it some other way. Because because when the universities get the money, they are the ones who are legally responsible. And many times, when there's something shabby going on, I complain to the university, sometimes the presidents, and even occasionally to the regents. It's never successful, but it's something that I need to do, because it's something that is really an offense against science, an offense against humanity, an offense against me as well as the taxpayers who support this. So I think the best thing is that the scientists themselves should be the ones who are supported not by grants, but by contracts.
Mm.
And usually with a contract, you have different kinds, but one is a cost plus fixed fee, where your costs are budgeted, and when you write a proposal as a contractor, you set forth what your costs are, your salaries and so forth, and then you set forth the amount of overhead. And so that overhead could be spent on rent for your lab, or for rent for the use of university labs or something like that.
I mean, it would definitely serve to make the scientist less of a vassal of the university, because I think that right now people get kind of pushed around by the desires of the university. The university takes they take half the grant money that's awarded just for maintaining facilities and putting it into the administration and whatever
the facilities
else.
aren't that great usually.
It was really funny. The place where we went, they had just built this really amazing new building. And after they built it, they realized that in the New York winters, there were these weird metal panels on the front of it, and the metal panels would grow ice like radiator fins, and then the ice would rain down on everyone below.
Wow.
So after they opened the building, they had to have all of this infrastructure to fix it. And I always just sat around and thought of how much money went into the design of that versus into the labs that were inside.
I can outdo you on that. My alma mater, which is the University of California at San Diego.
Mine as well. I went there for undergrad.
If you say that again?
I went there for undergrad.
Oh, okay. Well, you know the library.
Geisel, yeah.
If you look on Google for UCSD library, you find this incredible, beautiful, multi-layered structure, very modern look, and it was beautiful. Except that when they built it, they designed it without the concept of it being filled with books.
Oh no.
So they spent a vast amount of money to reinforce that whole thing.
Oh, that's interesting. Is that what those buttresses are?
Yeah.
Wow, I had no idea that it was originally built without them. That's very funny.
It was built to without the architects apparently considering the weight of books.
I mean, and this is so often the case that you see universities, they get money from research, which is an industrial business, and then they find ways to allocate that money for projects that don't necessarily feed back into the pursuit of greater truth. It feeds.
And another thing universities like to do is they like to use that money to fund all sorts of assistants and assistants to assistants in the administrative field, which is cumbersome. I mean, the time I was at UCSD, if I wanted to buy something, I mean, it was a problem. I had to write out an order, and somebody would then do one thing with the order, and it would go to somebody else, and somebody else who would finally maybe order the order. And where it is, now, if I want something, I either order it directly by on the web, or I pick up the phone and order it. And it's very simple.
How do you fund your research right now?
Well, I fund my research on my own nickel, because it's just physically it's impossible to do in the present circumstances. And the one thing it means that I can be entirely truthful. And if I was, there was this. See, what happened was when NASA did not renew my grant, I had basically a faculty position for research that depended entirely upon grants.
Which is the case for most faculty. That's why publish or perish is such a well-known.
Right. Well, in this case, my entire salary was based on grants, and when that grant died, so did my position at UCSD. So I was out on the street, and at that point, I thought about it, and I decided, well, I could try to get back into the university system and toe the line and not make, that was not me. I couldn't live with that. So I just decided I would produce what needed to be produced to keep the wolf away from the door and do science on my own. Because science doesn't necessarily have to be really expensive. And if you think about it, you can usually find a way to do something that is much less expensive. And so that's what I did. And I've been able to be honest. And so I'm not beholding to any organization, only beholding to my own values.
And where do you, for the most part, I mean, you've mentioned that you publish in PNAS, that you find these collaborations where you're able to place papers so that people can see them, but is there some kind of informal society where people are exchanging ideas that is the germ of a new institution? Because it seems like, these universities began, and they've been around for some of the earliest ones from, the year 400,
Yes.
year 500 or something. So they're old institutions. But eventually all institutions die. But are there germs of new institutions that are going to be around 1,000 years from now?
Well, let me, you mentioned that. Let me give you an example. Many years had gone by. So I think about 2012 or so, I decided to write a review paper about the georeactor, put all the information together. And there was a new Elsevier journal that had just started. It was open access, and so the first year or so, they were going to give it free of charge. So there wasn't a big backlog. So I submitted this paper, and it was handled by a geology professor at Oxford University. And he rejected the paper without review based on just nonsense. Now here, you're talking about the University of Oxford. Prestigious, old, and yet here is just the worst kind of deceit. So just for the fun of it, I pursued it up the line.
Are you saying you complained?
And they would not do anything. It's okay to be that way. Then I published it. I submitted it to Current Science, which is published by the Indian Academy of Sciences. And it was sent out for reviews to competent people who had some really good suggestions, and it ended up being published about 25% more length to it because of the suggestions that were made. So there are places to publish things.
They just might be the places that will be renowned. Because I think that there's this hysteresis to it, this lag, where the places now that are really the incubators of new ideas are going to be renowned down the line when people realize how useful these places were for incubating the ideas.
Well, I'm not sure that such exists. There are journals.
Sure.
There are journals who usually in third world countries.
Yeah.
Who
I think the preferred term is developing at this point.
Well, yeah. Okay.
Yeah, there's a new Cold War. We can go back to third world, I guess.
I'm educated now, but there are journals that maintain integrity, and they aren't too expensive for open access publishing. But you would think that, for example, the journals, PLOS1, I at one time had some high hopes for, until I actually submitted a paper there. and discovered that their editors were basically trained as editors at Elsevier or other journals and behaved in the same way. So I don't know that there is a place that is turning out good people. I think that the system is so badly corrupted. There are some independent people who have thoughts, and then one of the good things about what you're doing is bringing this to a forefront.
That's
because you were talking about the chap that thinks that the atmosphere was greater in times past.
That was our last podcast, actually. Oh, wait, not today's, but a week back.
Well, I'd really like to talk to him because I think I can demonstrate quite quantitatively that the atmosphere was greater in times past, or at least with reasonable assumptions. I was interested in that a long time ago, in fact, but the things you often think about things and they don't really. The ideas have to mature, and you develop them, and the evidence comes in, and so forth.
Definitely. I mean, we've been going for a while now, and I think that we've covered a lot of scientific ground. We've covered a lot of structural and institutional grounds. I think that it might be we might have gotten to a good stopping point of allowing this to be sort of the morsel that we digest until next time.
Well, we got through a lot more than I thought we would.
Yeah, this is really fascinating. I learned a lot. I read your book and I still learned a lot. So
you have a very good storytelling style. It's very linear. It's very organized. It's very clear.
Well, this is one of the point that I've been trying to make about science. Science, properly conducted, is a logical progression of understanding.
Yes.
You understand how one thing is with certainty. And that then opens the door to the next step with certainty. And so you progress. And so you can't just come up with an idea like a nuclear reactor at the center of the earth without going through the steps of how the earth formed and the state of oxidation and what it is matched to, and that you have literally a 1-to-1 mass ratio match with the abee meteorite, and the uranium is there, and so you see it's all a logical progression of understanding, and that's what makes a good story. Science is not a whole lot different than a really good movie. You go to a good movie and you see that all of the scenes are connected logically and causally, and you come out saying, hey, this was a great movie. Then you go to a movie where they're like pieces that are stuck together, and you come out, gee, I wasted my money.
Yeah, absolutely.
You know?
And may there be more of that kind of science. I mean, I think that that's a really big goal of our project with Demystifying Science, is that we want to showcase that it's possible to come up with visions of how the world works by following this very logical story-like progression. And so
and looking at the history, and the really interesting thing is that if everything is based on a previous understanding, you run into this problem time and time again, where if a little mistake was made in that understanding a long time ago, the snowballing effect can lead to all sorts of disturbances, which are very difficult to walk back on. And we see this almost with, all our favorite guests who have had really cool theories. It's just like, well, yeah, they have a good point, but it's just so hard to walk back on it for these institutional monsters. Like, I don't even see a road for them to do it a lot of the time.
That is so true. And one thing that I like to say is that you make discoveries by going back in time, and not with a Wellesian time machine, but going back through the literature.
Yeah, to find the thread.
Progressing step by step, because what you then find is that people make mistakes. Sometimes they don't have the data. Francis Birch didn't have the data in 1940. he could not have envisioned a nickel silicide inner core because there was no data in the literature. Okay, if maybe another time we can talk about the thermonuclear ignition of stars, which is a beautiful example of a mistake that was made. Because first there was the lack of data, but then the scientists involved, and we're talking big names now, Hans Bethe, von Weizsäcker, Edward Teller, they never looked back over their shoulder at what they had done before and thought about it in terms of what they had done after that.
And this is something you could imagine being built into graduate education, where there's actually time for looking at the history of your discipline. Because I know when I was going through grad school, it was just like, you just get in the lab and like get working on a project that's already in progress. And it's like, this is something we really missed out on, was having the ability. I mean, we did it in our own time, reading about the history of different sciences because we were fascinated, but it was very difficult to chip that time away. And I feel like students could really benefit from that.
Yeah. I mean, there's a long way to go to fixing these systems. I do think that it is possible, but it just has to be focused on a communal understanding of the value of science and how it works. And so hopefully this kind of provides some of that.
But we would love to talk with you some more sometime. I think that we should leave our audience with this for today. And we really want to thank you for coming on. This has been a wonderful conversation. And you just have so much work out there too. We'll try to post a lot of these references in the description, but you're pretty easy to find. And the paradigm shifts, it's on Amazon, right?
It's on Amazon.
All right.
And
it's excellent.
I also have a website, nuclearplanet.com.
Excellent.
That has access to information.
All right. Well, we'll make sure people find you.
This has been fun.
All right. Thank you so much, Dr. Herndon.
Very well.
Take care. See ya.
Bye-bye.